I want to demonstrate to you what the higher order function looks like. So this is the little bit that that I was referring to earlier about this dodgy network connection. So let's create a function called remote. Okay, so we say fun remote, and we'll give it a type parameter of a. Now, a higher order function is actually a function that takes another function as a parameter, right? So this is really cool stuff. Normally you would pass values in, but now you're passing a function as a value. So in this case, we'll just call it f, and we'll see that, say for instance, over here, we want to use this method, and we wanted to say remote product modulo sum. I'm just going to order these a little bit differently. Sorry, this does my brain in if stuff is not ordered properly. That's my OCD kicking in. There we go. That looks better. So if we have this remote function, we're actually passing in a lambda. You see that over there. So you're passing in a lambda into the remote. The lambda is capturing two values, product and sum, and then it's being passed into remote, and then remote will do something with it. So if we have to represent this as a parameter, it would be something like this. It takes no arguments and it returns an A. And this whole remote, okay, needs to return an int because that's what modulo returns. So it would be an A as well. So does that compile? Yes, it does. So here you can see, right, that is now a function that takes another function. Now, when I said over here that it takes no parameters, that it's a unit, I'm implying that there's none of this going on, right? If I wanted that to be an int, I could say here, int. You see, that immediately compiles. So now that would be an int. So if we want this to be a lambda without an input parameter, then that's so. Now this closure scope is quite an important thing. This thing actually captures these values, both of those values, and then transmits this whole function with those captured values. Notice it doesn't calculate first and then send it across. It actually sends this whole lambda across with these values attached. And then only once it gets inside of remote will it actually do this calculation. That's pretty cool, isn't it? So let's see how we can implement this. Right, so first off, let's assimilate this dodgy network connection. Let's just use something simple like a math.random, okay? So we say math.random, which is going to return a double between 0 and 1. And we say if math.random is bigger than 0.2, right, then we invoke this function. So you see that function over there? That can now just be invoked simply like that. Otherwise, throw an IO exception. Boom, just like that. So what we're saying here is that 80% of the time we'll succeed and we'll actually invoke this function in this case. And 20% of the time we'll have an IO exception and we'll blow up. Right? So let's quickly retrofit all of these with that remote function as well. So just go here and say remote, like so. And there we have it. We basically, now we have this remote call going on, and we're still getting back an int every single time. So all these values remain as they are. That's an int. All the others are ints. And it'll still do its calculation. So let's run this and see what happens. Right, so there's an exception. Boom. Let's run it again. This time it succeeded. If we run it again, we succeeded. Wow, lots of success. Come on, there we go. There's another exception. So the point I want to make here is that this is harmful, right? If you have something like this going on in your program and you're throwing runtime exceptions, because IO exception is actually a runtime exception, your compiler does not protect you against this, right? So this practice of throwing runtime's exception was popularized many years ago. I think especially in Spring Framework, they popularized the idea of propagating runtime exceptions and letting Spring handle this with exception handlers. You'd have to register a special exception handler and it would be able to handle your class of exception. Now, this is dangerous because you're delegating responsibility to something that's not your own. You're delegating responsibility of something as crucial as this to a framework. And you have to be lucky enough that you've actually registered a handler for the exception and made sure that you've actually done that. If you haven't done that, then suddenly you're going to start seeing explosions in production, right? Not just that, but throwing this exception at any point gives you the chance that it can terminate your whole program, right? And if you're going to call this multiple times from different call sites, you're going to have to remember to deal with the exception, to implement some kind of boilerplate with a try catch to catch this wherever you use this calculate method, you know? So if there's one place perhaps where you forget to do this, boom, you know, there you go. You've got another explosion in your hands. So this non-deterministic behavior and the fact that you're propagating exceptions up the stack means that your complexity of your program just spirals out of control. So the whole idea of the approach that I'm showing you now, and that I will be showing you now, is to contain that, to bring that back into something that you have control over. We don't want to see any exceptions blowing the stack. We rather want to see the error captured as a state and be able to deal with that in an elegant fashion, right? So let's get rid of that. Okay, so the next step for me would be to implement another higher order function. Let's just call this trap, okay? So I'm going to jump the gun a bit. I'm going in a bit of a different order to what I had on the agenda, but I think let's first implement this trap function to try and trap an exception, localize it, and make sure that it doesn't bleed up the stack. So let's create another higher order function, also type A, and we'll call it trap. And it's a very similar pattern that we're doing here. It's a function of unit to A, and it's going to return an A. And what we're going to do this time is we're going to do a try catch over here, right? So we're going to say try, and then inside that try, we're going to invoke that function. And then if something goes wrong, so we say E throwable, right? Then we'll deal with it. So at this point, we can do something. We can either return some kind of sentinel value, or we can do something else, right? But we can recover from the exception at this point and just go on. So let's go with the sentinel value. Now, this is a pattern that you see quite often. So for instance, I sometimes, I hate to say it, but I sometimes work in Bash. And in Bash, you have return codes. You don't have exceptions. You can't throw an exception, right? So you've got a return code that's going to be a non-zero value. And if it's a non-zero value, you better hope you've dealt with it, because if you haven't, then, hey, it just gets swallowed. So, but it also will terminate your program, right? So let's try and use something similar to that. Now, this trap can take another parameter called default, right? And the default can simply be an A. So if something goes wrong, you give it this default value, And if everything goes right, you simply invoke the function and return the A that gets passed in. Good. So now we've got something, a bit of a DSL that kind of helps us at the periphery of our application to immediately capture that exception, close in on it, and not let it move out to the rest of the world, right? So I'm just going to chuck this in here. I'm just going to say trap. Right. So what is the problem here? Oh, no value for no default value. So let's play around a little bit. Let's just use this. We're dealing in integers here. So A in this case would be an integer. So what about just returning a min value? Now this comes with a whole new world of pain. It's already better that we're not blowing the stack with an exception. But at the same time, we've now got this problem that we could be returning some kind of weird token value, either int minus or minimum value, or it could be like just a -1 or something. I'm sure you've seen something like this before. I mean, I've seen some nasty code in my life, and you know, people do all sorts of things, and this is one of the things I've seen before. So now this could totally break your calculation, because if something goes wrong in the network, product would be a -1, and sum could potentially be a -1, and then you get the picture. You're infusing incorrect values into this calculation. That's no good, right? That's not going to help anyone. So the next thing I want to propose after the sentinel value, it's a good idea, but let's add something more to it. Let's try and represent the error state as some kind of algebraic data type, an ADT. Let's try and create some kind of small class hierarchy that can represent a failure or a success. So in steps, sealed class option. Now you've probably heard of option before. You might have even seen it in other languages. You might have seen it in Java. They had the optional type. They still have it. It was not very well implemented initially because it didn't behave exactly in the way that you'd expect it to. Languages like Scala have the option. And I think in Haskell as well, there are many languages that have this. Here we have the option, right? And the option is of type out A. Good. Now, the fact that it's sealed means that the subclasses have to live in this file, right? And when you do pattern matching on instances of this one, the list is exhaustive according to what you declare in this file. So we are going to declare exactly 2 implementations. And when we pattern match over this, we don't need an else clause at the end. We can just use the 2 that we declare here. So the first one will be a data class, and we'll call it sum. It's also going to be of out A. Well, there we go. IntelliJ does it again. I keep seeing this happening, and I don't know why. I can't switch it off. There's nowhere I can click, so I'm going to just have to live with that. Sorry about that. Now, sum out A can encapsulate a val of A. This thing extends option A like so. So that's the first case. It's basically a wrapper class around a value of A. And to make this a bit clearer, we'll call this field get, so that we can just get it out. We should be able to just call on a sum, we should just be able to call .get and get its value, right? If there's a value, just give it to us. At the same time, we have the object called none, right? And this represents the state of something that does not have something inside of it. So this would be an option of nothing. So this is basically a base type in Kotlin. Nothing has no instances. You can use nothing to represent a value that never exists, right? So this is part of Kotlin, and we basically just instantiate the option with nothing as its type parameter. So because we've only declared these two in this file, this is now exhaustive for option. Option can only have a sum or a none instance instantiated and matched upon. Now, let's quickly take a step back. This is an interesting time to just stop here and reflect on some stuff. So what we're trying to do here is we're trying to use the type system. Right? We're using these types, the sealed class with its instances, to represent state. Now, in functional programming, you get different streams, right? You get like languages like Lisp, Scheme, etc., that don't really rely on the type system. Closure, that's another good one. Then you get functional languages that are typed functional languages. And they come with a whole separate paradigm called typed functional programming. Now, this is the branch that we are using here. We're augmenting functional programming with the type system to represent concepts, right? Or patterns, or we call them type classes. And these functionalities are things that we can represent in type hierarchies. So we're gonna delve into this a little bit more later when we get to the monad, because the monad is actually what we call a type class. It's actually something that can be represented by a group of functionalities which define that type class. It sounds a little bit confusing, but just stay with me. Right, so now we have our little type hierarchy. Option, sum, none. Now, let's try and use this in our code. All right, so where we have this trap, before we were just catching the exception and then introducing this dodgy default value, probably not great. So let's get rid of that. And now, instead, we are going to, instead of returning just an A over there, let's return an option of A. Okay, so now we're going to start using our new little class hierarchy over here. This is going to return an option of A. If it's a success, if we didn't blow here with this try catch, then we just simply wrap it, the result of it. So there's the function, unit to A, sorry, there we go, unit to A, wrap it in a sum. If we fail, then we just return a none. And that's it. There's our option. So here we're actually trapping the exception inside an option. We are confining that exception and kind of limiting the blast radius just to this tiny little piece of code and making sure it doesn't spread to the rest of our application. Good stuff. So let's get rid of these guys over here. Okay, good. Right, let's see what's happening here. So we're trapping these ones. Now, we see some compilation errors happening. Right, so this is going to be a bit nasty now, but bear with me, we're going to get past this. So product, obviously, is now using multiply. Multiply is using trap, and trap is returning an option of int. So now, all of these are no longer what we expected them to be. They're no longer ints, right? It's an option of int, and an option of int, and you guessed it, so you go on. So now, you're no longer dealing with that native value inside there. Now what to do? How can you get past this problem? So, this is where it becomes fun. This is where we actually really get into the fun part of functional programming. It's where we start writing functional combinators. So the first part was defining the ADT, algebraic data type, and now we're going to start decorating this with monadic functionality. Right? Okay, stick with me. So first off, let's quickly speak about functor. So functor is a type class. It's a basic type class. And you'll laugh when you hear what it is, because it's just a really fancy name for something really silly. It just means that a functor is something that is mappable. Anything that has a higher order map function on it is a functor. That's it. Big names for very simple concepts, right? A lot of us have been doing this stuff all along and never knew what it was called, but that's what a functor is. That's simple. So let's write a little extension function on the option, right? So we say fun A option, and we give it a map function, once again higher order function, that takes an A and transforms it into a B, right? So here we have a second type parameter called B, and this whole thing will return an option of B. Good. So what do we have? Let's take a closer look at this. So we have the option A, which could be a sum, which is a wrapper around an A. We have a map function that steps into the context of that option. It goes right inside of it, applies the function to what's inside of it, if it's a sum, transforms it, in this case, into a B. It's a pure function. It can't break. It just turns an A into a B. So it could turn an int into a string, or one data class into another data class, or an int into an int even. We don't care. The result, though, will be an option of B. Right? That's the functor. So let's pause there before we get to the monad. And let's try and wire this into our code example and see what effect this has. Now, this thing over here, multiply A comma B, returns an option, which means that guy has a map function on it. So I can say multiply A comma B dot map. Now, what do we get out of the map? We get a product, right? That's the thing inside of that option if we succeeded, right? Now, the next thing is the sum. So if in this line over here, we're going to go all nesty over here, but if we say add AB, another option, map sum, right? So that's already those two gone. Quotient, divide product by sum. Product, sum. Once again, map, what is that? Quotient. Right? Next one down. Next one we want to do is modulo. And modulo is also product and sum. Map it. And there we have our remainder. Kill that one. And finally, we have quotient to remainder. So we're going to slap that in there. And let's quickly simplify this. Get rid of that. No expression body. Okay, so here we go. We have all these nested things. At the end, we assemble our result. Now, we're expecting this to be a result, but we're dealing with options, right? So actually what we're expecting now is going to be an option of result. So if this calculate method fails for whatever reason, whatever step fails, we're expecting to see some option of result. So if we succeed the whole thing, if we manage to do all the calls without ever failing, we should get some result. And if one of these steps fails, we expect to see a none. That's simple. Now, let's hover our mouse over here and let's take a look at the damage. Right, so what we see here is something very different. We see we're not getting an option of result. Instead, we're getting an option of an option of an option of an option of a result. You see how cumbersome that is. So we need to do something to collapse all those options. Okay, right. In comes the monad. So the monad is very similar to the functor. It provides us with two new methods, right? Firstly, it's got a method called flatMap. And then it's got another method, which is less important in this case, called unit. So let's implement both of these. flatMap, also a higher order function, and unit. Right, so first let's start off with a flatMap. flatMap, A to B, option A, still the same as the last one, right? Higher order function takes an F, which is an A, to not a B. Okay, what this guy does is takes an option of B and returns an option of B. Okay, let me explain this. Map does not allow for error, right? It takes a pure function that goes from an A to a B. flatMap, however, takes another function that could itself fail, right? So if this is a sum and we flatMap, then the function that we pass into it could also return an option. Right, I hope you catch what I'm saying here. So this guy cannot fail. This guy can, because it returns an option. And then we deal with that internally and turn that into not an option of B, but just an option of B. So we'll get to the implementation of this at the moment, but can you see why it's called a flatMap? Why the flat is in there? We basically emit an option and still only emit an option over here as the return type. Whereas over here, we're just mapping straight. Over here, we're actually flattening that option, hence flatMap. We need another little function here, and we're just going to put it in here as a formality because it's not that important for our purposes. But in my sealed class, I'll create a companion object. You'll see now why. We are going to add an extension function onto the option called unit, and unit takes an A and returns an option of A. So it's kind of like a very simple factory method. It allows you to just lift a value A into an option of A. So we'll just instantiate a sum, passing in the value. Easy. This is a handy little one to have around when you're just fabricating new options. But the crucial one here that we are interested in is this flatMap. Now let's look at our example here that is still erroring out. So this thing over here is just the result. This bit over here is an option of a result, depending on whether this call succeeded or not. If this was a success, it would be sum of remainder, right? And then the remainder would come out here, we would map over it and return this as a result, not as a remainder. But now, let's take a look at the one above it. This is the one that introduces the next layer of error, possible error. So this function, if we look at this whole block over there, that function is an int to an option of result. Can you see that? So that's a perfect candidate for a flatMap, int to option of result. So let's try and replace this with a flat map. Now, hopefully you're going to see where I'm going with this, but can you see it's now found an option of an option of an option of result. There's no longer 4 layers of that, there's only 3. Let's go up another level. Let's flatten that one. What do we have? Only 2. And there we go, it compiles. So by using a series of flat maps on every option, we keep flattening out another layer of options. And finally, at the end, we simply map here, because this is the final option that we really want. We have this option, and this is what we return over here. Good stuff. So we are progressing. Now, what you see here, the combination of the functor and the monad, is often referred to as the monad design pattern, right? This taking away the layers of the onion until you're left with the kernel, so that you only have a single wrapped value, that is often called the monad design pattern. That's it. It's that simple. It's that easy. It's not a big deal at all.